I really wanted to squeeze in like getting
Again?
Yeah, I left the gym. So, yeah, just down and then just move 50 seconds to see if and maybe get a 40. No. Already to the way that this That's fine. Well, look, if they give you a day and a half notice, then that's just like a day or something. It should get.
Dude, I know.
I remember mine, so I can't know. Finish it like my project.
I said my specialty or my interest was design and mechanics of materials. So I got that.
Literally look at
My computer up here froze, and so you can probably hear me on Zoom, but the computer here froze. Let me see. Huh, that's weird. Yeah, so people out there, you guys can see me and hear me, but then the people in the class can't see me because you know, I use the Zoom to project my iPad. So let me see. Sorry about this, folks. So this is what I did in one of my other classes. It's a little bit jank, but it should work. Okay, this is super jank, but we can work with this for now. Okay. Oh, come up. Can everyone in Zoom still hear me? So I hate this because it has an really annoying glare for the people here in person, but this can work for now. I've had more technical issues this semester than all of last semester. Last semester was nice. No one was using this stuff. So you guys can still hear me? I can't view the chat at the same time. Okay, good. Oops. Okay, so the unfortunate thing is I can't view questions on Zoom space like this, and so I'm just going to stop every now and then and check the chat. But can everyone in the class see the screen? Yeah. So there's an annoying ass glare, but you know we'll have to bear with it. The Zoom literally worked just like an hour ago, and then now it's not working. Okay. Anyway, let's go ahead and pick up where we left off. Okay. So in other words, beam equations. Okay. And so far, you know, we've introduced this concept of the direct stiffness method, and the idea is that, you know, if we have these kind of structural elements, then if we can form the element stiffness matrices for them, then we can you know, solve equations of them. Okay. And so far, you know, we've only done cases where we have purely axial displacement. Okay. 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 It's a glare. Yeah, sorry about this. Okay. Okay, so axial displacement. So in other words, if we have an element like this, you know, we only consider cases where it can displace just left and right like that. Okay. And so that's fine for a lot of cases. And so for a lot of cases, you know, you can use pure truss elements or pure spring elements to represent your structure. Okay? But in reality, you know, we know that displacement or deformation of structural elements is a lot more complex than that. Okay. And so we know that we have a slender structure like this. Okay. We know that it can do a lot more than just displacing axially, right? And so for beams, we're actually going to cover the two other displacements, right? And so if we have a node here at the end, okay, in addition to axial displacement, we know that it can do displacement in this direction. And so we call this node 1. We'll call the node on the right node 2. And so the node on the left, we'll call that, or the one displacement here, we'll call that U1y, U2y, okay? And so those are displacements that are perpendicular to the element. In addition to that, we can also have rotations. Okay. Okay. And so we can have rotations of the two nodes, which we call theta 1 and theta 2. Okay. So let me go ahead and label these U1y, U2y. Right, so the formal name that we'll give these are called transverse displacements. Okay. And then theta 1, theta 2, we'll call these rotations. Okay. Okay. And so these represent kind of more complex displacement or deformation modes than what we've considered previously in our truss equations. Okay. And so the combination of these two, we'll call these our beam. We'll call this our beam element. And what we're going to focus on today and next Wednesday, because Monday's a holiday, is we're going to focus on solving these kinds of problems. Okay. Okay. Any questions on this so far? Yeah. Yes. Oh, actually no. Yeah. For this one, we'll use clockwise as positive. Yeah. Okay. Let me check the Zoom. Sorry, people here. Okay, no questions on Zoom. Okay. All right. Okay, and so these are beam elements, and so our first order of business, in order to solve these with our direct stiffness method, is to compute what the element stiffness matrix is. Okay. Okay. Okay, and so in other words, we're seeking a relationship between the forces on the element. Okay. And so we'll call this F1y. Oh, and of course, the coordinate system that we're using right now is assumed to be basically the local coordinates. Okay. And so remember the stiffness matrix. It forms a relationship between the forces on the nodes, okay, and the corresponding displacements. Okay, so we have F1y is connected to U1y, M1 is connected to theta 1, F2y is connected to U2y, and M2 is connected to theta 2. Okay, where M1, M2, well, let's start with F. So F's, of course, F1y, F2y. Those have units of force, right? So that's a transverse force, both in the local y direction. And then M1, M2, those represent a torque or a moment. Okay, and so we're saying that there's a relationship between torque and rotation. And then in between here, we have the element stiffness matrix of a beam. Okay. All right, and so our first order of business, before we can solve any any kind of problem with beams, is we have to determine what this element stiffness matrix looks like. Okay. And for these beams, we actually base this off of Ewar-Bernoulli beam theory Okay. Okay. So in other words, they're based off this equation here. Okay. Right. And so let's go ahead and define the parameters here. And so we have E still is the same as before. So E is our Young's modulus. Okay. I here is our moment of inertia. Okay. And that's the moment of inertia of the beam cross section. Okay. Uy, of course, here is our transverse displacement. Okay. And W of x here, this is some kind of distributed force. Okay. All right. And so, you know, there's a derivation out there which takes this equation basically, and then you know, and then you get the element stiffness matrix from that. And so I'm gonna, you know, just because we had a little bit of technical difficulties today, I'm gonna go ahead and skip that derivation. And I'm just gonna go ahead and skip right to the result. And so the element stiffness matrix for a beam, let's say after the magic of math, okay? After the magic of math, what we get is the following matrix. And so we have F1y, M1, F2y, M2, okay? This is equal to a matrix where we have EI over L cubed out in front, okay? And then this is gonna be multiplied by 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, okay. Minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, and 4L squared. Okay. This is multiplied by uy1, theta 1, uy2, theta 2. Okay. Where this matrix in the middle here, this is our element stiffness matrix for a beam. Okay. And I think the only thing I haven't defined here yet is L, but L is the same interpretation as our truss L. So L here is simply just the length of the element. Okay. And so that's the element stiffness matrix for a beam. Okay. And so now that we're equipped with that, we are ready to start doing problems. Okay. And so I have one more small thing to cover first, and then we'll see how this kind of fits into problems. Okay. And so any questions on this so far? Okay. Let me check Zoom. Okay, no questions on Zoom. Okay. Oh, actually, one thing before we do an example, let's talk about supports. Okay. Because now that we have, now that we're considering rotation as well as a degree of freedom, we have to be a little bit more careful with our supports. Okay. And so remember, our supports, what they are used for is to constrain the motion of our structures. Okay. Okay. So I've been a little bit lax recently, and so that I haven't really been talking about these with all that much strictness. And so let's categorize the three supports here, and let's talk about what they actually constrain in our models. Okay. And so the first is going to be the most restrictive support, which is a fixed support. Right? And so a fixed support will knock out basically all degrees of freedom. Okay? And so it's going to restrict both the X and Y deformations as well as the rotation. Okay? Visually, they look something like this. And so they literally look like a beam that's just jutting out from the wall. Okay. And so if we consider this node right here, right, so we'll call this node 1, okay? Then for a fixed support, we know that U1x is going to be equal to 0, U1y is going to be equal to 0, and theta 1 is going to be equal to 0 as well. Okay. And so fixed support, when the beam is stabbed directly into the wall, then those are going to have no displacement, no rotation at all. Okay. And so that's fixed supports. Okay. Yeah. So the user deformations and the theta is rotations. Yeah. Oh yeah. So I think it's good to define. So when I talk about displacements or deformations, what I mean is U1x, U1y. This is like the measurable distance that node traveled away from its starting position. And so if we had a like our 2D truss bars, and so if we had a truss bar that looks something like this, right? So it's a slanted one, right? And so it's going to displace by U1x, U1y. Okay, so if we say that U1x is equal to say 2 centimeters, U1y we'll say is 1 centimeter. Okay. That means after the load is applied, then that point is going to move to the right by 2 centimeters and up by 1 centimeter. And so I use displacement as kind of the more I would say exact term for it that's used in the literature, but displacements, deformations, I mean the same thing. The thing that's different here is rotations, which I think is the new one. So rotations kind of represent the orientation of the element at that place. Orientation, or another way that people think of it as, they think of it as the slope. Okay. And so this point here might displace by by certain flat distances, but it doesn't say anything about how the element itself is actually orientated. So and I'm going to exaggerate this just because otherwise it'd be really hard to draw, right? And so one way that you can imagine it is like the beam is kind of like bending over that way. Okay. And so it might be displacing up and to the right, but there's also some kind of twisting here that kind of changes the orientation or changes the direction of that element. Okay? And so if this would be like the original kind of axis of the element, but then the end is actually pointed this way, right? The difference in between these two orientations, that's the rotation. And you can have it the other way too. So if you have an element that looks like maybe like this, okay, and let's say it has an upward rotation, okay, here is the original axis of the element, and here is the direction that the end node is pointing, and then this change in orientation, that's theta. Yeah. So theta doesn't have any. There's no units for it, and so you'll see that when we solve for it, it has a units of radians, but it represents that. It just basically represents orientation. Okay, so those are fixed supports.
Are you just assuming that it's perfectly placed in the wall and that it could never fail in that area?
Well, it's not that it can never fail, and so you could have a stress here that kind of fractures it right there. It fixes everything, so it doesn't move and it doesn't rotate. So it keeps the same orientation in that. Yeah, and in fact, fixed supports are probably most likely where it's going to fail because you have something that's fixing it so much in place it has no leeway. And so if you apply a force right there, then you're going to get a lot of high stresses next to that because there's no give in that area. All right, so the next type of support that we have is a pin support. And so this is the one I've been using a lot in trusses. Okay. And so pin looks something like this. And so I usually represent it as a triangle. Okay. And the thing with the pin support is that the pin support will restrict, it'll restrict displacements. And so it'll make sure that that point stays fixed in the same point, but it does not restrict rotations. Okay. And so in other words, if we call this node 1 right here, okay, what we can say is u1x is equal to 0. u1y is equal to 0, but theta 1 is still free. And so, the rotation, the pin support is not going to do anything for the rotation. Okay? And the way that you can physically interpret it, and I draw this wrong every single time, you can imagine that it's basically exactly like a pin. Okay. And so the pin should actually be, in the center of the beam, so that it can actually rotate around that pin. But I never think about that, and so I always draw the pin support down underneath. But they mean the same thing. Okay. All right, so that's the pin support, and so the last support that we have is the roller support, which we talked about. Okay. And so the roller support, it's only going to constrict or only restrict one component of the displacement. Okay. And of course, that component of displacement that's going to restrict is in the direction perpendicular to the rollers. Okay. And so we've seen this before. And so we have a beam like this. Okay. I'll draw this one correctly. Oh, so I'll draw it correctly, but then I made a mistake right away. Okay, and so roller support, remember we denote it as like a support on wheels, okay? And so if this is the x direction, and this is the y direction, okay, then what we'll say is that the displacement is restricted in the direction perpendicular. So we say that u1y is going to be equal to 0. what U1x is going to be free. And since it's since it's free to rotate, then theta 1 is also going to be free. Okay. And so those are the three kinds of supports that we're going to be working with, you know, from here on going forward. So I wanted to talk about them just so that, you know, when you see them, you know, basically what to do, or what degrees of freedom to knock out when you're applying your boundary conditions. Okay. All right. Any questions on this? Okay. Let me check Zoom. No questions. Okay. Okay. So let's go ahead and do an example then, just to see how this all kind of puts together. Okay. So in this example, we're going to have a two beam assembly. And so on one hand, we're going to have a fixed support on one side. Okay, we're going to have one beam that comes over like this, and then another beam that comes over like this. Okay. On the other side, we're going to have a fixed support, or a pin support, excuse me. Okay. Right, and so that's going to be the interface between the two elements. And so this is going to be node 1, it's going to be node 2, node 3. So we're going to apply a mode P here. And so each element is going to have a length of L. Okay. And we're going to assume that both elements have the same Young's modulus and the same moment of inertia. Okay. In addition to this, we're going to have a moment that's being applied here. Okay. All right, and so in this case, you know, we're going to assume that the elements are purely beams. Okay, and so and so in other words, we're going to assume that there's going to be no axial displacement. Okay. And so the only degrees of freedom that we're going to be considering are the transverse displacements and the rotations. Okay. And so this example here is going to be just purely symbols. Okay. And so for this problem, what I want you to do is I want you to basically run through our process. And so write down the element stiffness matrix and set up the global system and apply boundary conditions. Oh, I'm sorry. So someone asked me at the beginning of class if clockwise was positive. I misspoke. So counterclockwise is still positive. So clockwise is, we're going to use the convention where clockwise moments, clockwise rotations are going to be negative, and counterclockwise rotations and counterclockwise moments, those are going to be positive. So I misspoke at the early beginning of class today. Because I'm looking at the example and it's positive. I kind of forget sometimes too. Okay. Any questions on this, on the setup for this example? Okay. All right. And so, there's no numbers here. So, of course we can't solve anything, but we can take it all the way up until the point where we can apply boundary conditions. And so let's go ahead and follow the same process that we've always done. Okay. Except now we're going to do it with beams. And so remember, the first step in our direct stiffness algorithm is to write out the element stiffness matrices. Okay. In this case, it's fairly simple because we have identical elements. The only thing that's different between them are the nodes that they operate on. Okay. And so let's start with KA. Okay. And so we have element A, element B. Okay. And so the element stiffness matrix for element A is going to be EI over L cubed multiplied by 12, 6L minus 12, 6L. We have 4L squared minus 6L, 2L squared, 12 minus 6L, 4L squared. Okay. And of course it's symmetric, and so you can write in the symmetric entries there. Okay. Element A here borders on nodes 1 and 2. And so we're going to have U1y, theta 1, U2y, theta 2. Okay. Right, and we have almost the identical thing for element B. And so element B here is going to be almost the same, except for the nodes that they operate on. And so element L stiffness matrix for B is going to be EI over L cubed. Okay. 12, 6L minus 12, 6L, 4L squared minus 6L, 2L squared, 12 minus 6L, 4L squared. Okay. Element B here borders nodes 2 and 3. And so this is going to be U2y, theta 2, U3y, theta 3. Okay. All right. And so of course, if you had numbers for this, you can plug in the numbers and get the exact values for that. Okay. But those are the those are the element stiffness matrices for this. Okay. All right. Any questions on this? Okay. Let me check Zoom real quick. Questions? Sorry, people. Where's my chat? Oh, chat. Oh, shoot. It's transcripting, I guess. Okay. Oh, question. So, any reason why clockwise is negative? Yeah, that's just the general convention that we take for for engineering problems. So, and so I think at some point someone flipped a coin and they said clockwise was negative, and then everyone just stuck with just for the sake of convention. Okay. All right. So now that we have the element stiffness matrices, we can go ahead and assemble them. Okay. And so in this case, we have 3 nodes, and since we have 2 degrees of freedom in each node, that means when we assemble everything, it's going to be a 6x6 system. Okay. All right. And so let me go ahead and do this. And so we have F1y, M1, F2y, M2, F3y, M3. Okay, so those are all our forcing elements there. Okay. Just to make things simple for us, I'm going to factor out an EI over L cubed. Okay, so it's going to be the same on both. And we're going to multiply this by our matrix here. Okay, so it's going to be U1y, theta 1, U2y, theta 2, U3y, theta 3. Okay. Of course, this is U1y, theta 1, U2y, theta 2, U3y, theta 3. Okay. So this is a fairly straightforward one. The 2 elements are just in series with each other. And so I'm going to go ahead and do this really quickly. And so I'm going to use this pink color here to denote element A. Okay. So this is nodes 1 and 2. Okay. And so that's going to cover these 4 degrees of freedom here. Okay. Meanwhile, element B Element B is nodes 2 and 3. Okay, and so that's going to cover these entries over here. Okay. And of course, everything else that's not highlighted or boxed is just going to be 0. Okay. All right, so let's go ahead and insert the entries here. Okay. And so for element A, we have a 12. Put that in a better place. Okay, we have a 12. We have a 6L. We have a 12, or minus 12, excuse me, and a 6L. Sure.
Yeah, just like right.
Okay. Yeah. Just let me know if the glare gets in the way. I'm kind of looking over here, but I'm not looking all the time. So yeah, just let me know. Okay. And so we have 6L, and then 4L squared, and then minus 6L, 2L squared. Okay. And we have a minus 12, 6L, minus 6L, 2L squared. Okay. Then we have a 12, minus 6L, 4L squared, minus 6L. Okay. And so those are all the entries for for that one. Okay, now let's do all the entries for element B. And so for element B, we're gonna have a plus 12, plus 6L, okay, plus 6L, plus 4L squared. Okay. Remember, anything that's overlapping, we're just going to just add their values together. Okay. I'm just going to fill in all the other entries just kind of pretty quickly. Okay. All right, so that's all the entries in the global stiffness system. Okay. And so the next step in this problem is to apply our boundary conditions. Okay. All right. So any questions on this so far? Let me just check the Zoom really quickly. No questions. Okay. All right, so I'm going to move it up. Let's see what's a good spot for it. There is no good spot. The glare is always in the way. All right, I'll just leave it down here for just one more second then, just to let everyone kind of catch up. Okay. All right. Actually, let me start talking about the boundary conditions here, just because it's we can kind of do that pretty easily. Okay. And so for this problem, we have two boundary conditions, or two supports, I should say. Let's start with the supports. And so we know that node 1 is fixed, right? Okay. And so that tells us that u1y is equal to 0, and theta 1 is equal to 0. Okay. And so that means we're going to modify these two rows of the matrix, okay, because they both correspond to node 1. Okay. And the other boundary condition that we have is that node 3 is pinned. Okay. And remember, a pin support, we get rid of the displacement, but we keep the rotation the same. Okay. And so this means that u3y is equal to 0, but theta 3 is free. Okay. And so that means we're going to modify this row in the matrix right here. Right. Okay, so let's go ahead and apply these changes. And so for for these ones, we're going to get rid of all this stuff here. Okay. We're going to put a 1 on the diagonals, and then 0 everywhere else. Okay, and we're going to put a
say one was fixed.
Yeah, one is fixed and 3 is pinned. Right, and so that's the first boundary condition. Okay, now for the pin support, we're only going to knock out the entries for this row here. Okay, so we have node 3. That's we're going to have 0, 0, 1, 0. Okay, and on the right hand side of the equation, we're going to have 0. Okay, all right. And so the last thing that we have to do here is we have to apply our modes. Okay, and so for this problem, if we can slide back up here to the problem statement, okay, you can see from the problem statement here that we have both modes being applied on node 2, right? And so we have a torque and downward force applied at node 2. Okay, and so we can apply that to our matrix. Okay. And so that tells us that F2y is equal to we're going to equal to minus P. Okay, and M2 is going to equal to big M, which is the moment that we're applying on this problem back from the problem statement. Okay. All right, so let's go ahead and write those in. And so for F2y, we're going to put in minus P, and then for M2, we're going to put in big M. Okay. Right, and the last piece of information that we need is M3, and M3 here is going to be just 0. Right, and so in theory, if you had numbers for all these things, and so you had numbers for the loads, you had numbers for all of the element properties, you can just punch this into MATLAB, and it'll give you a solution for the 6 degrees of freedom. All right, any questions on this? Okay. Let me check the Zoom just super quickly. There's a question. Oh, roll it. Yes. Yeah, I'm kind of balancing two things. So in class, there's like a big ass glare on kind of like this on this area of the screen right here, and this area of the screen. And so I'm balancing that along with just so that you kind of see things as well on the Zoom. So yeah, I apologize. I'm using a dock cam in the classroom right now because Zoom just like spontaneously just exploded on me in the classroom. Yeah. Yeah, for those of you in Zoom, I think I do have my mic on, and so if you need just something quick, just for me to scroll up or down, just say so in the mic, and then that's a bit faster for me than having, because I kind of have to close out my notes and view Zoom from there. Okay. Yeah. Sure.
Oh, wait, did you take out the moment at node 3?
Yes, I did. Yeah, so I set that equal to 0.
Okay.
So that's this one. That's this one right here.
I just thought I had seen M3 before.
Mm-hmm. I kind of took it out sneakily.
Okay, so all we have is the force at node 2 at the moment, right?
Exactly. Yeah. Mm-hmm. Okay.
Professor, could you hear me?
Yep, I can hear you.
Could you briefly explain why there's no horizontal displacement? I know we assumed no axial, but why are we assuming that?
Yeah. No, it's a good question. So, I mean, for this problem, the main reason we're not considering it is is due to our assumption. But in reality, you might have some sagging here, because if you pull this, God damn it, if you pull this beam down with sufficient force, then that's gonna kind of pull in these guys a little bit over here as well. And so in reality, you might have some axial displacements here, but right now our beam equation isn't equipped to handle it. And so in order to account for both transverse displacement and axial ones, we need a new element type, right? And so that element type is called frames. And so frame elements are going to be, what we cover next. And so frames are the most flexible element type, and so they can deform in any other way. But beams, we're only just concerned with transverse displacement and rotations. Okay. Oh God, it's stuck. Okay. All right, and so that's our example, right? And so even though our beam element stiffness matrix here looks different, our process is still the same. And so the next thing I want to go over just quickly is reaction forces. Okay. And so remember, reaction forces, these are the forces that are applied at our supports in order to keep our structure in static equilibrium, okay? And so, the way that we obtain these for beams is exactly the same way that we obtain them for trusses. And so after you compute, after computing the values of the displacement and the rotation, and so basically after you kind of fully solve the finite element problem, all you have to do is to take that vector of displacements and rotations and multiply it by your element stiffness matrix, the one that you had before you applied boundary conditions. Okay. And so they work in kind of the same way. Okay. And usually, even if the problem doesn't ask you to do it, it's not a bad idea to compute your reaction forces, because they're a good way to kind of sanity check your results. Okay. And so for this class, when I assign you homework problems, I give you the solution for that. But I make mistakes in my solutions sometimes as well. And so if you're getting a result that's different from my from my solution, try computing the reaction forces. And what you should see is that when you perform this calculation and you multiply your solution by the element stiffness matrix, if you get something that doesn't really make sense, like you have a reaction force on a node that didn't have any supports, then that's usually a good indication that you should probably go and check your results, because that's that shouldn't happen. Okay, any other questions before we do another example? I think this is the last example for today. Yeah, this is the last example for today, and then we're going to and then we'll wrap it up for today. Okay, let me check Zoom. Question. Oh, torque, yes. Yeah, so the big M's, they so the reason they have the symbol M is because they're supposed to stand for moments. But moments and torque, I consider them to be the same thing. Yeah, they have the same units after all. Okay. All right, so let's go ahead and do another example. Okay. And so this example, we again have a two element system, specifically a two beam system. Okay. Oh, I'm sorry. So there we have two beams and a spring. Okay. And so it looks something like this. And so we have a fixed support, just like our last example. Right, so we have two beam elements that are connected together just like that. Okay. So this is element A, element B, so node 1, node 2, node 3. Okay. This one will have numbers, and so we can actually compute stuff. Okay. So the lengths of both elements will say it's the same at 3 meters. Okay. But in addition to this, we have one more wrinkle. Okay. The end of the beam is actually going to be connected to a spring. Okay. Where that spring is connected to the ground. And so the bottom node of that spring we'll call node 4. And of course, the spring is represented by its spring constant, which is K. Okay. And of course, each beam has its Young's modulus and moment of inertia. Okay. Right, so let me go ahead and fill in the numbers for this. And so for the Young's modulus, we're going to assume it's going to be 210 gigapascals. Okay. I here is going to be 2 times 10 to the minus 4 meters to the 4th. Okay. And K is going to be 200 kilonewtons per meter. Okay. All right, and so now that we have numbers on this, what we can do is we can actually solve this. And so let's solve for the nodal displacements and rotations. Okay. And then after that, let's solve for the reaction moments, our reaction forces. Okay. Okay. That's a good spot. All right. So that's the problem. So any questions on the problem setup? Okay. All right, and so this is almost a carbon copy of the last example. The biggest difference here is that we actually have a spring. Okay. And so springs, remember, springs are just like trusses, and so springs are only limited to axial deformation. But you can see we've taken the spring and we've rotated it 90 degrees, such that when the spring displaces in the along its axial direction, that actually matches up with the transverse displacement of the beam. Okay. And so we're doing a little bit mixing and matching here, but but it's all good because the spring, because we rotated the spring 90 degrees, and so the displacement of that spring matches up with the displacement of the beam itself. Okay, so first step, just like we always do, we're going to start with the element stiffness matrices. Okay. Oh, we'll call the spring element C. All right, so let's start with element A. So element A, Ka. We have just a standard beam here. Okay. And so we have EI divided by L cubed multiplied by 12, 6L minus 12, 6L, 6L, 4L squared minus 6L, 2L squared minus 12 minus 6L, 12 minus 6L, 6L, 2L squared minus 6L, 4L squared. As you can clearly tell, I have not memorized this, and so I'm kind of reading that off my notes as well. These things are hard to remember. Okay. Okay. And of course, since this is connected to nodes 1 and 2, then we're going to multiply that by u1y theta 1, u2y theta 2. Okay. And then same thing for KB. Okay. Okay. And in fact, I'm just going to be lazy. I'm just going to draw an arrow here. So these are the same. Okay. And node element B here is connected to nodes 2 and 3. So this is going to be u2y theta 2, u3y theta 3. Okay. All right, so those are the element stiffness matrices for the two beams. Next, let's go ahead and work on the element stiffness matrix for the spring. Okay. And so for a spring, we know its element stiffness matrix is just K minus K minus K, K. Okay. And the spring here is connected to nodes 3 and 4, right? And remember, a spring can't support any rotation. And so the only thing that we're going to have here is just U3Y and U4Y. Okay. Okay. And so those are our three element stiffness matrices. Okay. So again, pretty standard stuff. For the element stiffness matrices, we have our derived expressions, and so a lot of it's just kind of plugging and chugging and just making sure you got the right answers or right numbers for everything. Okay. Any questions on this so far? Okay. All right. And so those are element stiffness matrices. And so the next step is assembly. Okay. And so we're going to assemble all this into a single system. So let me go ahead and write down all of the nodes here. Okay. Or all the degrees of freedom. And so we have F1y, M1, F2y, M2, F3y, M3, and F4y. Okay. And so we have kind of a unique case here. And so we have actually an odd number of degrees of freedom. So you can see that here, this is a 7 by 7 system. Okay. The reason for that is because the spring cannot support any rotation. And so at the point where it's connected to the ground, well, in the end, it's not going to matter because it's connected to the ground. But this part here cannot rotate. Okay. And it cannot rotate because it's a spring. Okay. And so that's why we kind of end up with an odd number of degrees of freedom. Usually it's an even number because each node supports 2 degrees of freedom. Okay. Right, so we have U1y, theta 1, U2y, theta 2, U3y, theta 3, and then U4y. Okay, so we have U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y. Okay, so let's go ahead and do everything that we've done before. Okay. And so first we have element A. And so element A is nodes 1 and 2. Okay. So element A is going to be this block right here. Okay. I'm just gonna use black for the rest of the lecture because I think that's easiest to see with the glare. Okay, then we have element B, and so element B is nodes 2 and 3, and so that's going to be these things right here. Okay. All right, so let me go ahead and fill this in first, and so let me put in EI over L cubed out in front. Okay, and so this is going to be 12, 6L. Minus 12, 6L. Okay. 6L, 4L squared, 6L, 2L squared. minus 12. Yeah. Minus 6L, 6L, 2L squared. This is a 24. This is a 0, 0, 8L squared. Okay. Minus 12, 6L, minus 6L, 2L squared. Minus 12, minus 6L, 6L, 2L squared. Okay. It's going to be 12 minus 6L minus 6L 4L squared. Okay. Okay. All right, I'll give people a couple minutes just to kind of catch up on this one.
How come we multiply it by the EI over L cubed on the outside if we have our K's still?
Yeah, so when we so that's why I'm saving the case for a bit later. So and so it's you kind of have to pick your poison. And so you can either not have the thing on the outside and then have EI over L throughout the entire thing. Which you can do. It's just a little bit annoying to write. But I'm just gonna multiply the K's by the inverse of EI over L cubed, basically. Right. Is there any questions on the Zoom? I can't minimize it because people are still writing it down, but is there any questions? Someone turn on their mic. Okay, I guess I'm going to assume that means there's no questions. Okay. All right, so that's all the contributions from the two beams, but of course we still have the contribution from the spring left. Okay? You have to be careful with this because it's deceptive because even though we have a 2x2 system, remember the spring doesn't interact with any of the rotational elements, and so that means the spring is going to be in the U3 slot. Okay, so it's going to be this one right here. It's going to be in the U3 U4 slot, which are going to be these two right here, and then also in the U4 slot, which is going to be that one right there. Okay. And then since we have this multiplier out in the front for EI over L cubed, we need to account for that. And so that assumes that we multiply this through the entire thing. And so if we have our spring constant here, that means we have to multiply it by the reciprocal of this. Okay, so this is going to be plus K. Let me zoom in on this. Okay. And so this is going to be plus K. Actually, let me go ahead and remove this box. All right, so it's going to be plus K times L cubed divided by EI. Okay. This is going to be a minus K L cubed divided by EI. Okay. This is going to be a minus K L cubed divided by EI. And it's going to be a positive K L cubed divided by EI. Okay. Okay. And so I made those adjustments, to the K's because they don't have those beam coefficients out in front. Okay, and so they're their own thing. And so if we're going to have the beam coefficients out in front, that means we have to adjust all our other coefficients, in turn. All right. And so of course, we can fill in the rest with zeros if we were. Yep.
Where did you place that exactly? Minus K L cubed E over I. It's between theta 2 and U3Y.
Right. Yes.
Which slot is it on?
So it's in the U3 and U3 slot, and then U4 U3, and then U4 U3. Yeah. So it skips over all the thetas because the spring doesn't interact with the rotation. Yeah. I think I skipped over space here. Okay. All right, and so there is our assembled matrix. Okay. And so of course, the next step in this problem is to assign boundary conditions. Okay, so I have a convenient spot up here to write out what the boundary conditions are. Okay, so the boundary conditions, if we go back up to the problem, we can see here that we have a fixed support at node 1, right? And a fixed support at node 4. Okay, so those are the only supports that we have. Okay. And I think I forgot to give the loading. And so the loading is applied on node 3, and it's a simple force. Okay. And so the force has a magnitude P, where P is 50 kilonewtons. I always forget to put the force in percent. But we'll come back to that. Okay. And so for a fixed node at node 1, remember our fixed supports here, they knock out both the displacement and the rotation. Okay. And so both of these rows are going to be, we're going to knock them out. And so, we're going to replace this over here by 0. Okay. And then everything else we're going to replace by a 1 on the diagonal and a 0 everywhere else. Okay. And then the other place where we apply our fixed support is on node 4. Okay. And so just like we did up there, we're going to eliminate the spring constant terms that we worked so hard to put in the first place. Okay, so we're going to put a 1 on the diagonal and 0 everywhere else. Okay. All right, and so those are our supports. Okay. Just down a little bit. Because that's that part of the spring is attached to the ground. All right, and so now let's go ahead and add in our load. And so our load here is only a purely vertical load applied on node 3, and so that means that F3y, it's in the negative direction, so we have a minus P here. Okay. Meanwhile, we have no other loads applied on the other nodes. So we have a 0 here, and a 0 there. Okay. And of course, our P, remember, is 50 kilonewtons. Okay, so we can go ahead and fill that in. And then all of the other variables we can plug in as well. So we have the Young's modulus, remember, our Young's modulus was, I think, 210 gigapascal. We have our moment of inertia. We have the length of all the elements. And of course, we have the spring constant as well. Okay. And so we're fully equipped to kind of plug in all the numbers here and then solve it in MATLAB. Okay. All right, so before I jump to the MATLAB solution, are there any questions on this? Let me check Zoom. Okay. All right, and so if you go ahead and plug in all those values, then we get the following results. Okay. All right, so let's start with the result at node 1. Let's remember node 1 is fixed, and so there should be 0 displacement as well as 0 rotation. Okay. So the units for the rotation, when you first compute the number, it's usually given to you in radians. Okay. And so that's what we have there. Okay. Next, we have the values for the displacement at node 2 as well as this rotation. And so this is going to be minus 0.02 meters. And then the rotation is minus 0.012 radians. Okay. Right. Next, we have the displacement at node 3. So this is where we have the most action, because this is where our load is applied. And so the displacement there is minus 0.0638 meters. Okay. So a good 6.4 centimeters about, so pretty decent. And then the rotation here is a minus 0.016 radians. Okay. And then U4Y is 0 minus, U4Y is 0 because it's fixed. Okay. All right, so we're just about out of time, and so, but I did want to give you the reaction forces. And so remember, if you take this solution and you multiply it by your global stiffness matrix that you had before you applied boundary conditions, you can get the reaction force. And so let me give them to you just really quick, just for your own reference. Okay. I know we're out of time, so I'm going to be as fast as I can. Okay, so we have reaction forces. So F1y is 37.23 kilonewtons. Okay. M1 here is minus 893.62 kilonewtons meter. Okay. F2y and M2 are both 0 because there's no supports and no loads there. Okay. F3y is equal to 50 kilonewtons because that's where we are applying our load, minus 50 kilonewtons. Okay. M3 is equal to 0. Okay. And then finally, F4y is a positive 12.77 kilonewtons. Okay. And so node 4, which is attached to the bottom of the spring, is applying an upward force to establish static equilibrium. Okay. All right. Any final questions on any of this before we wrap it up for the week? Okay. Let me check Zoom real quick. Sorry, Zoom people. Okay. All right. So that's all I have planned for today. And so I apologize again for the technical difficulties. So hopefully everyone was able to see and hear okay. So remember, Monday is a holiday, and so Monday we don't have any class, but I will be having office hours on Monday, and so, but they'll be purely virtual office hours. So I'm not going to drive to campus just to sit in my office for an hour. And so, if you have questions on the homework or just questions about anything, you can pop in the Zoom room, and I'll be happy to help you out for that. Okay. All right, and so that's it for this week. And so thank you guys for tuning in today. Thanks for bearing with the technical difficulties. Hope everyone has a good weekend. And I'll see you guys in a week from today. Thanks, guys.
I just want to make sure I place in this right.
Mhm.
So I have like my 80 plus 45 stiffness.
Yep.
And then it's like F1x, F1y, U1x, U1y.
Yep.
That'd be right.
Yep.
F1, F2, U1, U1.
Yep.
Okay, and then this one should be F1, and then it should correspond to 3.
Yep. Yep. These look right. So there should be. So I mean, for these ones, they all kind of keep together.
Yeah, 2 by 2s.
Yeah. So there's 2 by 2, and then there's a gap of a 2 by 2. They're 2 by 2.
Okay, yeah, because that's got to be F3, F3s and U1s together, and then
Yep.
F3s and U3s together.
Yep.
Cool. That's it. I try to finish this one off today.
Okay. All right. Good night, guys. Have a good weekend. Good night.